You're listening to Worth Electronics What's Up Radio Podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with our leading industry experts and Worth Electronic technology specialists. We're going to shine a light on some interesting topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up Podcast. A few years back, Worth Electronic created a power inductor that completely altered the electronics components industry. The WE-MAPI power inductors offer a high saturation current, high permeability, and low resistance, but even more, at one time, it was the world's smallest coiled metal alloy power inductor. But the market for bottom termination components, also known as BTCs, representative of QFN and DFN package, is rapidly increasing in the electronics industry because technology is becoming smaller and cheaper. BTCs have brought a lot of new challenges in design and assembly processes when these package types were introduced in the market. The large areas of the solder terminals bring a lot of advantages with them, such as dissipating heat of the component. But if the assembly process is not properly adjusted, then this can cause voids under the component. The amount of voids can be influenced by different adjustments, such as solder paste with special solvents and grain sizes, thickness of solder paste print on land pattern, the solder profile, the land pattern design, the solder stencil design, and of course, the surface of the PCB. In today's podcast, we'll be discussing the work that is carried out to evaluate the challenges of voids on the WE-MAPI and other DFN products. Different techniques and tests have been carried out in order to resolve this issue, such as custom land pattern designs, optimizing reflow profile, custom stencils, push-off tests, and the list goes on. Voids in solder joints are a consequence of outgassing from within the solder joint when the solder paste is in molten form. One could say that voiding is proportional to outgassing when the solder paste is in molten form, and this implies voiding is really dependent on flux chemistry. Voids are influenced greatly by wetting of the solder, meaning better the wetting, lesser the flux entrapment in the solder joint in the molten state. So in other words, if we can exclude the flux from within the solder joint, the outgassing of the flux will not contribute to the voiding of the BTC packages. Overall, the wetting process is of more importance than outgassing. This can be taken care of by using higher melting energy, which comprises of high peak temperature and longer dwell time. Now, when we talk about custom land pattern, a common technique here is to implement a crosshatch pattern on the thermal pads of the larger QFN package ICs, such as the processor ICs. Similarly, the idea of custom land patterns of different geometries and orientations was also tested. Now, this aim was to see if the wetting process of the solder paste was actually faster than the outgassing process, which would result in stronger joints and voids reduction. The land patterns were purposely made a little bigger than the footprint of the WE-MAPI. This was in order to get a meniscus and to accommodate for the outgassing process. Keeping in mind the points mentioned earlier, land patterns of various orientations and pitches were also designed. Pre-tests were carried out to check as to which land pattern would yield the best result. So after the pre-test, we were able to see that the 180-degree rectangles and distributed squares showed to have the best results. In our experiments, we used lead-free solder paste, or SAC alloys. It's very common understanding that reducing the solder paste will help in minimizing voids. This is usually created by making a pattern on the stencil on a solid land pattern. At the same time, you should also account for the lesser flux per unit area with respect to the land pattern due to the smaller solder paste printing. As a result of the reduced flux per unit area, the solder paste does not have enough flux to avoid the solder paste from drying out and oxidize during that reflow process. Ramp to peak, or ramp to spike, is the reflow profile that was developed considering the small solder paste print deposit sensitivity and higher temperatures. This profile is basically aimed at reducing the thermal stress and total heat input, but this profile is seen to strain the solder paste, especially for smaller paste deposits, and in order to avoid voiding to a certain extent, a soak profile was implemented. A reflow profile was designed with an extensive trial and error method to actually implement these points. First, the implemented reflow profile was ramp, soak, spike, or RSS. The linear ramp rate was approximately 1 degree Celsius per second. This minimizes the overall number of problems that are associated with the reflow process, such as solder balling, solder beading, and hot slump. The soak zone, this is where it's important to minimize voiding. It helps with a faster wetting process than outgassing, and in turn helps in avoiding the tombstoning effects. We also have to keep in mind the light weight of the MAPI components. Next, peak and time above liquidus, or TAL, were in accordance with the recommendations of the standards and data sheets. Our peak temperature of 265 degrees Celsius and a little longer TAL of around 90 seconds. During the cooling stage, a drastic cool down is actually desired in order to obtain a finer grain structure. A slower cool down will result in a larger grain structure, which typically exhibits poor fatigue resistance. So a cool down ramp of almost 6 degrees Celsius per second is used. It should also be noted here that the reflow profiling was in accordance with IPC/JEDEC J-STD-020D, so you should refer to the same for further details. Now, before going into the results of the conducted tests and our experimentations, we should first discuss some results from the MAPI products with the original land pattern. In our first attachment, Figure 1 in this podcast, we can clearly see the lake voids. These voids result in weakening the joint, and they act as thermal insulators, which results in a faster increase in temperature in the inductor and also during operation as they obstruct the transfer of heat from the inductor to the PCB. For best results, and judging by our CT scans, the land patterns should completely eliminate lake voids, but smaller voids still prevail. We'll be discussing this a little bit later. We also want to note that the stencil thickness of 120 micrometers was used, and the rhombus shape patterns visible in our CT scans were actually due to the shape of the land pattern and not the actual voids. Our smaller voids were calculated to be 14.96%, as so far there is no standard or norm that actually specifies the proportion of voids in a solder joint for these BTC components. According to IPC 610, 30% of voids are allowed for BGAs, so we took this as a reference for our own analysis. To check for the terminal break strength of the components, push-off tests were carried out. The push-off force with the normal land pattern was just around 60 newtons. After looking at the results from our pre-tests, extensive testing with distributed square land pattern for further analysis was actually carried out. And to preview our push-off test results, simply click Figure 2 attached in this podcast. Furthermore, in order to validate our results, the same testing and analysis pattern was applied to a large number of specimens. Here, the solder paste was changed from what was used in the pre-tests. The fine pitch capability of this solder paste used for statistical tests was 0.3 millimeters. Two stencils of 100 and 120 micrometer thickness were used. For statistical tests, different pitch sizes on the distributed square land pattern were implemented using 0.1 millimeter and 0.2 millimeter in order to compare and study our results. From our statistical tests in the CT scans, we can see that soldering finish on the land pattern with 0.2 millimeter pitch is a much better option than on the land pattern with 0.1 millimeter pitch. This is because of the fine pitch capability of solder paste, which was 0.2 millimeters in pre-tests and 0.3 millimeters in statistical tests. Therefore, the solder finish with the 0.2 millimeter pitch land pattern is better. We should also note here that the pitch of the stencil and the land pattern are always the same, and our area of voids on the right pad was calculated to be 21.1%. Also noted in our CT scan is a rather blank area resembling a void. Now, this is not actually a void, but rather a place devoid of solder paste itself. This is due to the land pattern design and bad solder finish because of the higher fine pitch capability of the solder paste than the pitch size of the land pattern itself. The area of voids on the left pad were calculated to be 14.2%. In summary, we were able to successfully avoid lake voids in our bottom termination components, or BTCs, with a dual flat package. There was no decrease in the solder joint strength, rather a dramatic increase in the same, from around 60 newtons to 120 newtons approximately. Using a vacuum reflow oven or any other non-oxygen medium reflow will help reduce voids to a larger extent. All in all, voids are a boon as much as they are a bane, like friction, for instance. We need to remember that voids are an unavoidable phenomenon when it comes to the bonding of two different metals in a molten state in a non-vacuum environment. They basically act as stress absorbers or relievers and avoid the propagation of cracks within the solder joints. Complete absence of voids will actually result in higher tension in the joints, eventually leading to development of cracks. What we need to be concerned about are the lake voids. These trap air and they act as thermal insulators, so this in turn leads to a faster increase of the effective temperature rise of the component and also a decrease in the overall solder joint strength. These lake voids were effectively eliminated without influencing any electrical parameters, such as DCR, rated current, and saturation current, by the techniques we discussed earlier. Attached images are available in most podcast streaming networks. To view all images, visit www.we-online.com/podcast. To download the complete application note discussed today, visit Worth Electronic online at we-online.com/appnotes. You're listening to Worth Electronics What's Up Radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with our leading industry experts and Worth Electronic technical specialists who will shine a light on topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast.